Today we'll be taking notes on the types of waves. One type of wave is called a transverse wave. One thing that we know that is true about all waves is that they transport themselves through what we call a medium. Waves or disturbances travel through a liquid, gas, or solid. And when the medium moves a certain way in comparison to that of the energy transfer or the wave, we call it a different kind of wave. For transverse waves, it's where the medium vibrates perpendicularly to the direction that the wave is traveling. You see this when the medium moves side to side, or it creates an up and down movement. This is true for all string instruments, such as a guitar, a violin, or piano. Every time that you pluck, hit, strum any of these strings, it creates a wave that transports itself in one direction, and it moves the liquid, gas, or solid particles perpendicularly. Radio waves and light waves are also examples of transverse waves. Here's an example of a person who is holding a rope, and the rope is being moved up and down, and the motion of the rope is, for example, the medium. So it's either the way that the air, the liquid, or the solid is moving, and then the energy transfer is actually moving from her hand to the direction to the right. So the direction of the wave or the energy transfer is perpendicular to that of the motion of the particles of the medium. Here is a moving example. So if the wave is traveling in the direction from left to right, you notice that the particles of, example, the water is moving up and down, which is a perpendicular direction to that of the direction of the wave. Longitudinal waves are where particles vibrate parallel to the direction of the energy transfer. So this is where the medium goes in the direction of the wave. There is a backward and forward movement. So sounds are an example. When sound waves move through solid, liquid, and gas, you'll see that the direction of the wave is going from left to right, and there are and pretty much the particles, such as the water particles or the air particles or even the solid particles, are also moving in the direction that the sound wave is traveling, or any wave. Sound is the best example of a longitudinal wave. What you'll notice is that there are areas that get compressed and areas that get expanded as it moves through from left to right. Here are sound waves moving through air, and you'll see that the particles here, when you have a tuning fork and you hit it and it makes that little sound, it will vibrate, and the air particles will vibrate because of the sound wave moving through the medium of air. And what you have here is a compression and an expansion at various places as the wave moves through the medium of air, and we call those compressions and expansions. Here is a moving example of multiple particles that are moving from left to right. What you will notice as it moves, this is again the direction of the wave, the direction of the energy, as well as the direction of the particles. So this is an example of a longitudinal waves. What you'll notice is there are compression spots where the particles kind of bang together and get squished, and then they also do expand and get further apart. As you work your way through over from left to right, it also shows little areas of kind of like a pattern of compression, expansion, compression, expansion. There is a third kind of wave called a standing wave, and this is a wave that reflects. What I mean is that the wave is transferring itself through the medium, either be that water, air, or solid. And then what happens is when the wave or the energy transfer gets to the end and it hits something, then it will reflect back on itself and it meets up with the original wave. This creates a distinct pattern that looks like the disturbance does not move through the medium at all. For example, here we have a rope that is attached to a fixed end. And if we are moving the rope up and down with a low frequency, this is what you would see. It would come, so you would have the wave move through, but then there would be a reflection back. Down here, the frequency becomes higher, and the wave will go through, but then it would also go backwards, and it reflects itself back upon itself. Here, it's where it looks like it has 1, 2, 3, and then it comes back 2, 3. So these are 3 different kinds of frequencies from low to high. And this is just showing how the wave, the energy transfer, gets reflected back. The energy transfer here gets reflected back. And also here, it gets reflected back. However, because of this reflection, it looks as if there is no movement of the disturbance or the energy transfer through the medium because of the reflection. Notice that when you are doing this, because it doesn't even look like it's moving, you create these areas and points right here where it doesn't seem to move. And this is why we call them a standing wave, because it doesn't look like it's doing anything, that there's no change. So what you see here is that you have these nodes, which are points that don't seem to move. And then there are antinodes, which are points on the standing wave that have the largest amplitude. And remember, amplitude can be anywhere from the medium, the middle point, the equilibrium point, to the lowest part, the trough, or it can also be the highest point here, which is the crest. So these are the amplitudes, also known as the antinodes. And then the nodes are the center points that don't seem to move at all. Here's an example of a standing wave. So notice at these points here, these are the highest and the lowest points. These are the antinodes. And then those are equidistant. They're in between each node. So antinodes are found in between each node. And remember the nodes, take a look at this while I start the video back up. You'll see that the nodes don't move. So nodes, antinodes, this is a standing wave. And this looks like a higher frequency of oscillations. And we'll just watch this as the frequency starts to change, and you'll see fewer wavelengths. Okay, here's the frequency is starting to change. It's going to become lower frequency, so you'll see fewer waves. But you can still identify where the nodes and the antinodes are. These points right here that are stationary are called nodes, and then the antinodes are the highest point, and the lowest point from the midpoint for the highest part right here is the amplitude, and the amplitude here. So both of these points are called antinodes. The frequency will change again and become even lower. And what you'll see here is that the node is here and the antinodes are over on either side. So this is an example of a standing wave. All right, thanks for watching. Have a great day.